the talk that we're going to be doing today is 90 minutes to machine learning. And this is going to be that's an ambitious goal. I want to acknowledge that right now. 90 minutes to learn machine learning is a profoundly ambitious goal. But in doing so, my goal is to provide an intro to the data science program. Okay, so my name is Ryan Orsinger, and this is 90 minutes to machine learning. Right? So let's get started. Our agenda for the day, first things first, let's talk about a little bit more about what the heck is Codeup. And then after that, we'll do a big picture overview of what is data science, what is machine learning, how are they, where do they overlap, where do they not overlap? And then we'll actually get into some machine learning tools and concepts with Python code. Okay, so I'm going to be demoing some Python code in like the third part of the day, or the third part of the workshop, and then we'll conclude with next steps. So this is your roadmap for what to expect. I'm going to talk to you about what Codeup is and how we do things, and then we'll talk about big picture overview of data science, machine learning, what they are, what they aren't, and then we'll actually look at some Python code and an example project, right? So let's get started with, let's get deeper into this. So we know where we're going with that agenda. Let's talk about what I want to, if I could package everything into one slide and give you the high level summary of everything that we're going to be doing in this workshop. Here we go. This is our high level summary, your takeaway for the day. Folks, I hope I'm not the first person that's told you that data is the new oil. If I am the first person who's told you that, then I can't even take credit for the term. It's pretty popular right now. Data is the new oil. Data skills are very highly prized by employers and organizations, and demonstratable, solid, reliable data skills, not just surface level stuff, right? We will be building a machine learning model in less than 90 minutes today, but that's just the tip of the iceberg. I'm going to cut a lot of corners. So if you know anything about machine learning already, you'll notice that I'm cutting some corners to make everything fit, right? But I want to make sure that y'all are able to have an intro, a conceptual intro and a little bit of the detailed intro in 90 minutes. But that 90 minutes is not the same thing as a 670-hour program. And that's what Codeup is a 670-hour program that takes 5.5 months, and that's about 30 hours a week of lecture and lab time, which adds up, right? This is an immersion program. And my punchline for you is through Codeup, you can indeed start learning and data science and machine learning, and you can start working in data science without a PhD, without a master's degree, right? There's quite a bit of gatekeeping. What we found at Codeup, however, is that most employers care that you can do the work, right? So that's what we do when we work with employers to design our curriculum and our offerings. We reverse engineer what employers need and want so that they're more likely to hire from Codeup, right? So this is our high-level summary, right? So why Codeup in particular? There's lots of ways to get started in data science, right? There's formal education ways, there's certificate programs, PhD programs, master's programs, etc. My answer to you is one word. It's results, right? It's results. And let's take a look at some of the numbers. These are pretty fresh. So 94%, this is, let's see, this is 18 out of 19 of the graduates from July of 2020 are placed with an average salary of 68K. And like, yeah, this last year has been pretty rough for a lot of companies, right? It's been pretty rough on folks in the looking for jobs, regardless of their technical skill set. But that's pretty impressive, 94% from July. And then the class that graduated 4 weeks ago in January, 25% of those individuals have accepted offers. So that's not too shabby. That's not too shabby. And so why Codeup? Results. And again, that point, through Codeup, you can learn data science and machine learning and start working in the field without needing a master's degree or a PhD. It is in fact a possible thing. Okay, so that's a bit more about the why Codeup piece. Yeah, and in the chat, Stuart is linking to an event, another event that we're having called "You Don't Need a Degree for a Career in Tech." It doesn't hurt, right? It certainly doesn't hurt, but with how we design things, we are in fact placing people without advanced degrees. Right? Cool. So show me the code. I promised y'all 90 minutes to machine learning. Let's do that. Here's what I'm going to do. I'm going to fire up my editor with some code here, and I'm going to share with y'all a link in the chat here. So the link in the chat here will go to this code notebook that I am demoing. And you can make yourself a copy. So when you navigate to this Google Colab notebook, all you need is a Google account, right? If you don't have a Google account, then I recommend you make one. And this notebook is a combination of text and Python code, and it's called a Colab notebook on the Google platform. To make yourself a copy that you can edit on your own, go to File, and then save a copy in Drive. Right? Super easy to get started with these Colab notebooks. Okay, File, and then save a copy in Drive. And in the text instructions here, there's some guidance on how to do that. Okay, so why are we here? Intro to Codeup experience, big picture overview to data science, like we talked about, and an intro to ML concepts and some tooling. You'll have a little exposure to Python. I'll demo some data acquisition, data preparation, which are huge. I will do a tiny bit of data visualization, and then we'll make a predictive model, a machine learning predictive model, and then we'll evaluate how well that model performs on new data. Okay. So we talked about why Codeup, and the answer is results and outcomes for students. I want to make sure y'all heard when Stuart was talking about the tuition refund guarantee. That is a real thing. That is not just marketing lingo. That's stuff that the refunds that the company has done for folks where things didn't work out. But y'all saw by the numbers, data science's hiring rates are pretty groovy right now. Right, so that's awesome. That's excellent to be able to say. I don't know about y'all, but I did not have that experience with any of my university experience. Right, they didn't guarantee anything. But what we're here for is what is data science, and let's take a look at this visual here right quick. I've got a Venn diagram with 3 overlapping circles, and when we're talking about data science, we're talking about an interdisciplinary science at the intersection of programming, math and stats, and business and domain experience, right? So in data science, we have a lot of statistical modeling and statistical tools. Does that mean that you need to be the best statistician that ever made a statistic? No. In fact, you don't need a PhD or anything in statistics. Same thing with programming. You don't need to be a professional programmer already, but you need the ability to learn fast, right? 22-week-long program. We've got a lot of content. So being able to learn enough programming, enough stats, and enough domain expertise means learning agility and learning speed is pretty important, right? So right at this intersection of programming, stats, and knowing your business or knowing your domain is where we can apply the scientific method, right? The scientific method of look, guess, test, conclude, look, guess, test, conclude, over and over and over. And we're having our programming language run our statistics for us, right? We're not calculating anything by hand. We're not calculating the area under a curve by hand or anything like that. We're having our programming language do that for us. And in a nutshell, I like to talk about data science as life after Excel, or like what can you do, or how can you work with data that's too large for Excel, or that Excel you'd have to like custom program the math to do what you need to do. So it's totally possible to do machine learning in Excel, but I don't know how many of y'all have ever tried to open up a corrupt spreadsheet before. They're very fragile documents, right? Anybody ever have a corrupt spreadsheet before? A corrupt spreadsheet file? Maybe Google Sheets has made that a thing of the past. Awesome. I'm going to pause for questions at this point right now. Go ahead and hop off mute and let me know if you have questions right now. Okay, cool. If y'all don't have questions, I'm assuming I could quiz you on this and you can tell me what data science is tomorrow, right? The biggest takeaway, I think, is there are many different definitions of data science, but the definitions that are all in accord are that it's an interdisciplinary science, right? So let's keep going. Because there's some spots in this Venn diagram, right? Let's talk about what those different spots are. So we have programming chops, that's a computer science on the left, math and stats, business and domain experience, data science at the overlap of all three. So how does data science relate to machine learning? How does that relate to data analysis? How does that relate to traditional software? Well, traditional software exists in this space where we're applying computer science methods to solve business problems, right? Think of traditional software as everything from mobile apps to applications to help you calculate your taxes, to logistics applications, any kind of normal application, right? Is traditional software, and that's there's sometimes traditional software has some math and stats in it, and usually that's it when we have some data science going on. It is entirely possible to conduct machine learning and build machine learning models without knowing anything about the business or without knowing anything about the domain. And I would call that, at least personally, I would call that just machine learning in isolation rather than kind of integrated with your understanding of the business or your understanding of the domain. Data analytics, traditional data analytics, business analytics, business intelligence, there's tons of overlap between traditional data analytics and data science. What's the difference? The difference is how much programming you're using and how much work you're getting to do in an automated way through a programming language. So the boundary here between data science and data analytics can get a little fuzzy, right? There are jobs that say data scientist, but you're doing data analytics work. There's jobs that say data analyst, but you're doing data science work. I wouldn't get hung up on that too much, but know that there's quite a bit of overlap. And the big difference is that with data science, we're doing quite a bit more programming rather than relying on like traditional data analysis tools where the tool will try to do as much as it can for you. But with when we add more programming in, we can take analytics and meld them with software and also have some machine learning right at the center there. All right, cool. Let's keep going. So if machine learning is the intersection of computer science and stats, and what is machine learning? There are, in broad strokes, machine learning is the process of automating the ineffable. Automating the ineffable. What do I mean by automating the ineffable? If we're building a video game, generally, like if we're building chess or a game of checkers or something like that, there's the spot for machine learning isn't in building the rules of chess. We already know the rules of chess, right? So we can program those rules into an application. Just like if we're building TurboTax software or advertising software or something like that, we know what the rules are. and we send in data to a classical program to get answers, right? So think of my example here would be tax software. The tax rules are the rules of your taxing entities, right? Whether if it's a state or federal thing, or a city tax or something like that. And then we send in data for your class, and then we get answers back, right? Rules and data to classical programs, and we get answers back over and over and over. We do this all day long. Now, how is machine learning different? Well, I'm going to focus on a broad part of machine learning called supervised learning. And in supervised learning, we feed an algorithm tons and tons of data, and the data that we're training on has some answers, has some labels. So in a way, it's kind of cheating, right? But if we're trying to make a predictive model, we need to build our predictive model based on something. It can't just guess all the time, right? So it has to have some sort of target and lots of raw data with those targets labeled. My example of this would be handwriting recognition, right? It would be very easy to build a classical program to recognize my handwriting, and then we'd have to get more rules in the classical programming to recognize Reginald's handwriting, and then we'd have to add more rules to recognize Ravinder's and Stewart's and Babush's, right, handwriting. Well, with machine learning, we can feed in lots and lots and lots of examples of handwritten digits along with some answers, so we can train a statistical predictive model to match patterns. That's the goal, is pattern matching, really. Pattern matching and distance measuring with linear algebra in so many words. So what does machine learning give us if we provide data and answers? It gives us rules. That's what the model is a set of rules to apply to future data coming in, or to apply to data that the model has not seen. And that's our definition of a good model, is a model that performs well, not just on data that it trained on, but on data that it's never seen before, that it's encountering for the first time, right? Okay. So this is the biggest difference between machine learning and classical programming, is this idea of what can we get from the raw data itself. And there's tons of data where we already have the answers for kind of like our training data, just our data to train a model. Then we get a set of rules, then we apply that rules on future data. Okay. And that's a big deal, because classical programming can't solve the problem of things like facial recognition or handwriting recognition or predictive text, but machine learning can solve problems like facial recognition, handwriting recognition, grammatical fixes to your email as you're typing, right? Autocomplete. For machine learning, classical programming is a bit more constrained because we have to know the rules already. So this opens us up for a lot of capabilities in many different fields, right? I mean, if we have a pattern matching machine, and we can take that pattern matching machine, bring it to medicine, bring it to business, right? Bring it to nonprofits, etc. So where does machine learning fit into data science itself? I'm going to pull up a flow, kind of a diagram here. We'll start on the left. And in this example, this example will be detecting credit card fraud, right? So whenever there's any kind of credit card transaction online, people fill out a form on a web page or fill out a form on an application. They buy something, right? We're all pretty familiar with that process. What ends up going on with the servers that are running Amazon, or they're running whatever service you're using, eBay, whatever, they're gathering tons of data, like where you purchased from, what kind of browser you were using, what kind of computer you were using. And if we are the credit card company, we are also gathering information about all the customers' purchases, right? So this is the first the first real step in a data science project is, what are you trying to do? What are you planning to do? Well, we're planning to detect credit card fraud. Then we need to gather data. So we're gathering tons and tons of transactions, right? After we gather and clean that data, I guarantee you, your data is dirtier than you think. We need to start exploring and analyzing that data. And this is where a lot of traditional business intelligence or business analytics comes in. This stage in data science, we call this exploratory data analysis. And we're looking for the story. What does the data show? What do the data show actually? What are the trends? What are the things we're trying to predict? Well, we're trying to predict fraud. What are the drivers of that? Did somebody use a credit card 100 times on the same website? Or did they use the credit card in 2 different physical locations at the same time on opposite sides of town, right? 5 minutes apart. We could look for that there. From this data exploration stage, we can do one of 2 things, and we'll probably do both. Right out of the gate, we can probably make some sort of report or recommendation on what the indicators of fraud are based on our analysis, right? In this analysis, we're doing lots of visualizations, data visualizations. We're doing hypothesis testing. We're doing aggregation of the data. We're grouping by things. We are seeing the relationships of the different variables of the data, right? The time of day of a transaction, how many times the credit card was used. If the credit card company thinks you're in Texas, but your credit card was used in Canada, right? Was it used to buy gasoline, or was it used on an eBay store or something like that? Once we've analyzed our data and we have some pretty good indicators and predictors, drivers of our target in this case being if a transaction is fraudulent or not, it's at that point, folks, that we can start building a predictive model, right? And in that predictive model, we have to turn all of our numbers and labels into pure numbers, and we will build a predictive model that goes through this process, right? We know if some transactions are fraudulent or not historically, right? Based on, if we are the credit card company, we know if something's fraudulent if a customer contacts us and says, hey, I noticed this charge on my card in UK and I'm in Berlin, or something like that, right? So if we have enough data and enough answers for the data, we can train a predictive model, pattern matching model, to learn the rules, kind of the shape, in a way, of how a valid credit card transaction is different than a fraudulent credit card transaction. There's characteristics that are statistically significant that make them different, right? So by learning on past data, we're able to build a predictor. And if we have a predictive model, we can enable action with that predictive model. That's what people are after. This is what people want. Customers don't care about the rest of this data science pipeline or your model. Customers care about getting the text message that says, your credit card was compromised, but we fixed it already. You have a replacement card with a new number in the mail already. That's what customers want, right? They want really kick-ass customer service, but we can get that great customer service with human beings, right? But if we have a predictive model, we can get that going at a large scale, right? Cool. We'll leave this on the screen a little while. We'll be working with a little bit different data set for our example, and we'll be trying to solve a different problem than credit card fraud. But looking at this is a very classic example of building a machine learning product, making a report internally, collecting the data, analyzing it, making a report internally. If we're the credit card company, then building a predictive model, and then working with the rest of the IT team and the rest of the software development team to put that model into production, get that model working on the internet live so that customers can get account alerts. All right. How are we doing? How is the pace, folks? I want to check in with y'all on the pace of things. so far? Is the pace okay?
So far, it's good for me.
All right, cool. Excellent. Thank y'all for the feedback. All right, so looking at we've seen some of the upsides, and all of us in here, we've seen some form of a data product that has tried to help us, whether if it's autocorrect or fraud protection, right, or facial recognition. We've all seen some sort of data product. So let's talk a little bit about some of the challenges in machine learning. Machine learning is not magic, and there are some pretty big challenges. And the number one is poor quality data, just crummy data, not enough of the data, insufficient quantities, and non-representative data. That's a huge one, right? If we build our model based on business activity in South Texas, that data of South Texas transactions for this credit card company is going to look very different than somebody in Connecticut. Very different, right? And that will look different than somebody in Paris, right? So we need to make sure whenever we're building a model that the data that we're training our model with, building our model on, is representative of the data that model will encounter in the real world. Otherwise, you're wasting your time, literally wasting your time and energy. And because we're talking about automated processes, it's important to recognize that if we have any kind of bias coming in to a system, to an automated system, we will get bias out of that system. And what do I mean by bias? Well, there's two kinds of biases. There's cognitive biases that arise from being human, right? Some of those cognitive biases can lead to things like prejudice, right, or blind spots in human beings. So we need to be very aware of that. But also there's a big list of different kinds of statistical biases, and those don't necessarily arise from just our being human. Those arise from our methodologies themselves. The statistical biases have to do with if we measured the data in a certain way, right? I asked y'all for check-in on pace a little while ago. I asked y'all if the pace was okay, right? Well, we have a reporting bias because I didn't get an answer from everybody. I only got an answer from folks who were ready, willing, and able to speak up at that time, right? So statistical biases, we ran into one already, right? And self-reporting bias is another bias. If people report on their own experience, they have a tendency to inflate the positive or say things that aren't quite as accurate, right? So statistical biases exist because of methodologies. Cognitive biases exist, and there's not like a formula. There's not a piece of math that fixes this for us, right? This means that we have to be ethical in our approach and mindful, right? And I bring up the challenges in machine learning because the punchline is whatever a model learns, right? There's no learning involved. It's not cognition. It's not actually intelligent. These are pattern matching machines. But whatever the pattern matches, it will keep doing. There's no intelligence, there's no cognition, there's no, it's not like the Terminator, right? There's no self-awareness or anything like that. We're just talking about pattern matching. So yeah, garbage in, garbage out is the challenge. So we're talking about data science, we're talking about machine learning. What are some of the skills and some of the different ML models that we'll cover in the data science program? This is way too much for today, but in the data science program at Codeup, we cover, and in quite a bit of detail, Python programming, SQL, and SQL for databases, statistics, storytelling with data, visual storytelling, data storytelling, collaboration, interview skills, version control, presentation skills. Those are huge. So it's not just hard skills, but soft skills as well. And when we look at specific methodologies, we work with classification, which is something A or B, or C or D or E. We work with regression, which is predicting where a number will be. That's really good for like predicting sales, for example. Time series analysis, if time is the component, is the explanatory variable in a data set, we focus on time series analysis. And we also do another type of machine learning that is a little bit different than what I introduced to y'all before. It's clustering, and clustering is a little bit different in that we're not providing rules along with the data. We are just looking at the raw data to see what kind of clusters exist. Go figure, with a name like clustering, we're looking for what clusters exist in the data already. And this is really cool because this can lead to finding, this clustering can lead to finding relationships that might not be immediately evident to us. We also have a module and project on anomaly detection that's looking for very extreme measurements. Why are they there? Is this a typo, or did we really have this many sales this day, right? And then we work with natural language processing, which is really cool. Natural language processing is where we treat words and letters like numbers, and we look for statistical similarities between documents, between emails. We can use this to determine sentiment, like if an email is happy or grumpy, or if a survey is angry or delighted or something like that. We can also use NLP to see if one author wrote two different documents, right? Which is pretty wild. We also work with a technology called Spark for big data, and we introduce neural networks and deep learning as well. At the end of the Codeup process, we end with a final project that we work with students to help design. So at each stage of the game, every one of these main topics, we have a big project around, and then at the end of the course, we have a final project. Okay. All right, so let's keep going. What kind of ML are we going to do today? We're going to do some classification machine learning, and we're going to be using a very beginner-friendly and very approachable model called a decision tree. A decision tree kind of works like playing 20 questions with our data. And the data that we're looking at is human resources information from a company, whether containing information about each employee and whether or not they're still with the company, right? Some other examples of what classification can do in machine learning is facial recognition, handwriting recognition, recommendation engines for movies you might like, or products you might like, or songs you might like. So you've probably seen things out there like a YouTube recommendation, Netflix recommended movies, right? They're probably using some sort of classification going on. All right.
Hey, Ryan, real quick, there's a chat about bias in clustering.
The takeaway is there's bias everywhere. So clustering doesn't wiggle free of that. Why is there bias everywhere? Because number one, cognitive biases because we are human, and number two, statistical biases that arise from our methodologies. And there's not some magic calculation that can solve these things. You got to have your head on straight, and you got to have a good head on your shoulders. Guided ethically, right? And we can't just do something technological in isolation, right? We have to pay attention to what the trade-offs are. I hope that answered the question. Yeah, there's bias everywhere. Deal with it. With statistical biases, there's more that we can do, but this is not a workshop on statistical biases. That we'll do that one later. Okay, cool. So we are at the halfway point in our show, time-wise and content-wise. So at this stage of the game, folks, we are going to play a role-playing game together. We are going to play imagination. We are pretending that we are a data scientist at a consulting company. It's our first month on the job, and our supervisor comes to us and they say, "Hey, HR needs our help. What we know is that employee attrition is expensive, it's bad for culture, and it costs a lot of time to recruit new hires, to hire them, train, and onboard new employees, right? So we need your help because you're the fancy data scientist, right? Here's a spreadsheet. Here's a spreadsheet from HR with all the information we have on employees for the last year. And we need you to determine if an employee will stay or go. What are the best predictors of attrition? So are the employee responses good indicators if people leave or not? What can we learn? What can we learn from this data from HR? Okay, so this is our scenario. We're pretending we're on the job. We're pretending our first project, it comes to us from the human resources department. They want to know, okay, build a fancy machine learning model and determine which, who's going to stay, who's going to go, so we can try to coach people into staying with the company, right? So in this project and in any data science project, we have to start with planning and ask critical questions. What's the business goal? Who are the stakeholders? Why should we care? Why does the business care? What does the data look like? What are we trying to predict? What data is the data we have? Will that be valuable at predicting what we're trying to predict, or is it just data that's not connected to the thing we're trying to predict, right? Our plan for the data set, really we need to understand, this is what HR is asking for, is for us to build a predictive model if a specific employee is going to leave the organization or not. So they can try to, I don't know, buy them ice cream or something like that. So we've defined our goal. We're going to build a predictive model. Again, it's very ambitious in under 90 minutes, especially since we've been just covering groundwork so far, right? Once we acquire the data, we do need to clean it and prepare it. I've got a demo of that for you. We do need to define the target variable. In our case, that's the thing that we're trying to predict. In our case, that's whether or not somebody's still with the company or not. And this is for like a consulting company, right? And then we have to do something. This is very, very critical, that this will separate more the data science side from the data analytics side, and that's preparing an in-sample chunk of data and some out-of-sample pieces of data so that we can build a model based on a subset of the data and evaluate how that model performs on the rest of the data that it hasn't seen before. So we're building pattern matching on somewhere between 70 and 80% of the original data, and then what's left over, we'll use that as our out-of-sample data to evaluate if the model's good or not. And this is critical because if you use all of your data to train your model will be perfect. It will be perfect, but only for the data you gave it, and you won't have any other data to work with until brand new data comes in, and we wouldn't know that our model could be good or bad. So we have to create a scenario where we have brand new data by taking a section of the data and putting it aside. Okay. So I'll show y'all what the data set looks like momentarily. Right now, let's go take a look at the data dictionary. Data sets that have a data dictionary explain what to expect, what the columns are and what they mean. So in our data set, we have a column called attrition, and this specifies if the specific employee left the company in the last 12 months or is still employed. Then we have monthly income, education level, which is a number here. So this probably came from a survey or a drop-down, right? People didn't type in their own stuff. So some college, bachelor's, master's, PhD. And then we have some self-reported columns, work-life balance. So this is an employee survey with self-reported data. My work-life balance is bad, good, better, or best. Same thing with job satisfaction, self-reported data. Low, medium, high, very high. And looking at these pieces of data, we have percent salary hike. So that's good. We should probably, I think looking at people's salary is a good way to ask this question in HR. Same thing with business travel. If somebody lives on an airplane, they might not want to live on the airplane. So these are the columns that we have in our data. Do y'all see anywhere at this planning stage where there could be a challenge to building a machine learning model already, right out of the gate.
The willingness to share your satisfaction would be dependent upon your fear of losing a job as well.
Bingo, bingo. What does that do to our data? What does that introduce?
A bias towards high or very high.
Bias, yeah. Self-reported data, generally, and this isn't just for Western, like European cultures. I've seen this replicated globally. There is a tendency on self-reported data to self-report to make things look better. So yeah, we have this spot where there could be bias in these pieces of data, right? There might also be bias at the company around education level, just depending on the culture of that company. Our theoretical company here may value certain levels of education differently. And in that case, that's not statistical bias, that's bias coming from the organization, right? If the company only hires people with certain degrees, then it's going to skew the data, right? Or if the company kind of nudges people to, oh, you should go back to school. Oh, yeah, then we're introducing human bias, right? Are y'all with me that there's human bias, cognitive bias in the self-reported, and then there's, and that's also a statistical bias in the self-reported data. And then with something like education level, and gosh, if we had other columns on here, we might have other cognitive biases as well, right? So let's take a look at the data. Show me the code. Show me the code. Here's what I'm going to do. I'm going to import a whole bunch of data science libraries that are going to help us. We're going to go down this list really quick. If this is your first time seeing these, that's okay. If you're in the Codeup data science course, you're going to use these almost all the time. We'll use pandas and NumPy. These are like, you put pandas and NumPy together, this is like Excel on steroids. And then you put Matplotlib and Seaborn together, those are our visualization libraries. And then everything with sklearn has something to do with our machine learning toolkit, okay? So I'm gonna run my notebook, and it may take just a second here. All right, so we've performed some imports. The value of importing code is so that we don't have to build everything from scratch, right? By importing sklearn for machine learning, we don't have to take a whole bunch of fancy math that makes machine learning models and write and convert that math into Python. That's already been done by the authors of sklearn, right? Same thing with NumPy and pandas. We don't have to build a bunch of Python code to help us clean data or read data. Those libraries exist to do that for us, right? So I've defined a function here called split that will split a data frame. Think of a data frame like a database table or a spreadsheet, a big, huge spreadsheet with potentially millions of rows. The split is how we create the in-sample and the out-of-sample data. Okay, let's keep going. I'm going to read my data from a CSV file. A CSV is comma-separated file. That's like a spreadsheet export. So let's take a look at this data. Let's look at this together. We have all of the columns that we talked about already. It looks like monthly income is, if this is a US company, this is in dollars. We have the self-reported columns, education, work-life, education is a measurable, work-life balance and job satisfaction are self-reported. And then we have some columns that are like categories. The attrition is the thing we're trying to predict, so yes or no. The business travel, there's 3 values in here, rarely, sometimes, and never. And we need to do some data preparation on this. So this is pretty clean data, right? I don't have dollar signs on the money. I don't have employee names here, but think that each row here is a single individual employee. So the first row could be Jane, and then the second row of this data set would be Bob, right? So each row is a new employee, an individual employee. Okay. So looking at this right out of the gate, I'm happy to see lots of numbers here. Machine learning models do well with numbers. That's what they're built from and built to work on. But I see a couple of string columns like the yes or no and the travel rarely, frequently, or never. So our machine learning algorithms aren't going to be able to work on plain old words, right? So we have to do something about these plain old words. And this is part of our data preparation stage. My logic for turning these words into numbers is my attrition that's a yes or a no. I'll turn that into a 0 or a 1, right? And then with the business travel, if we only have 3 outcomes, we could use 3 different numbers. Or I'm thinking traveling rarely and traveling never are basically the same. If you like, gosh, I hate to be a traveling salesman or anything like that living on a plane these days, right? So let's try to simplify that. So I'm going to put some Python code in front of you. What I'm going to do is convert my yeses into ones. You see what I'm doing here? I'm saying, hey, the attrition column, make sure to set the new value of the attrition column to be a transformation. Apply this function to transform things. So turn yeses into ones and nos into zeros. So we're basically making that yes or no a binary, right? Binary is great for computers. And then we need to clean up the other column names so that rather than just the travel with 3 options, all I care about is if people are frequently traveling or not. So I will do it 1. And I'm making a design decision here. I've made a command decision. I'm going to output 1 if they travel frequently and 0 if they travel rarely or never. So let's take a look at our new data. First employee has an attrition value of 1. That means that this employee left the company in the last 12 months, but they did not travel frequently. They either traveled rarely or never. So I'm kind of like rounding down on those frequent travels if it's never or rarely, okay? And again, I want to recap the reason why I've done this. Machine learning models only work with numbers. It's how they work, right? So everything, including just plain old words, we need to convert those into numbers in order to move forward. Okay. All right. Questions so far? I'll pause a minute, give y'all a moment to hop off of mute and ask any questions at this time. The stage that we're doing is preparing the data a bit.
I did have a slight question about maybe I'm overthinking this, but on the output, wouldn't you would want to do something like if yes, 1, if no, 0, and if else, register like some kind of error?
What do you mean? I'm curious what you mean, Ray.
So like if the data was input with some other variable other than yes, no, you wouldn't get just a 0 if something other than no was inputted. You would have. Yeah. Okay.
Yeah. What you're not seeing is the fact that I've already explored this data to make sure the attrition column doesn't include maybe. In fact, I'll take a little peek at this. We can say the attrition column at this stage in the game, df.attrition .value counts. We can see what the value counts are, and we see that there's no other options. Yeah, so definitionally. So yeah, I'm not exploring this data for the first time.
Gotcha.
I'm doing the cooking show where I pull it out of the oven for you. Does that make sense, Ray?
Yeah. So you're our Gordon Ramsay of code, I guess.
Yikes! Yikes!
I respect Gordon Ramsay. He's a great guy.
I don't know him personally. Yeah, I'm doing a lot of getting to the point in this demo, because my goal is very ambitious to make a machine learning model with y'all in an approachable way in under 90 minutes. So what you didn't see before was me going through the data set and actually looking, hey, when I look at the business travel column, what are my different value counts? What if there's like 5 value counts in here? Well, no. It looks like most people travel rarely at the company. Most, and the smallest amount, don't travel at all. But I made a design decision here not to make 3 outcomes, but to make 2 outcomes, just to loop in the rare travel with the frequent travel. And that was a design decision on my part. Yeah, and we'll look a little bit more at the data set and the visuals.
Quick question. Hello?
Yeah, go ahead.
So once you've got the data cleaned and everything, how do you determine between like causation and correlation?
Ooh, man, that's tough. I can. Was that Xavier?
Yeah.
We can measure correlation real easy. All that means is that things move together in a linear way, right?
Right.
Causation is much more challenging to actually measure. What we can look at is we can try to control for things. It's hard in a lot of places to make a controlled experiment, right? If we were doing epidemiological research, we would be applying causal methods, right? But we'd also be able to control the situation completely. In this case, I can't control the situation completely. I have survey data from employees from the last 12 months, right?
Yeah.
I don't have a control group or a variable group. The closest thing that I can do to that is split the data up into my in sample and out of sample.
And so as a data scientist, is it like, is your main thing to just present, like clean the data up, like analyze it and give it to someone, or is it to like draw conclusions?
All of the above.
Okay.
Yeah, all of the above. And where different roles spend their time may vary, right? There are folks in data science who do much more of the data cleaning and data acquisition. On the other hand, a lot of folks will do a lot of data visualization and modeling. It just depends on the individual, depends on the role.
Okay.
Yeah.
Thank you.
Mm-hmm. All right. Yeah, great question. That was a really good question, Xavier, and that's a hard question because causality versus correlation. Correlation is easy to measure. Correlation ain't causation, but at least it's something, right? The most important thing is that we don't confuse correlation for causation when we see it. Yeah.
Right.
Yeah. So my example here where I've cleaned the data up just a little bit, turned my attrition yes or no's into zeros and ones. I've collapsed my 3 values for frequent travel into a binary. Consider that this is the teeny tiny tip of the iceberg, right? This data could be really gnarly. We could have, with the income, we could have dollar signs, commas, decimal points, right? In the percent salary hike, if the data is pretty ugly, we might have percent symbols that we'd have to take care of, and then we'd have to remove the percent symbol and convert this into a number data type. So data cleaning is critical. It is very critical, and I'm giving you just a teeny tiny taste, right? Once I've cleaned the data, and we have that we have all numbers at this point, I'm going to split my data up into a couple of different chunks. With that split function, I'm going to make my training data set. That's about 75% of the data. And train will be what we analyze, what we train our model on, what we explore visually. And then these other 2 data sets, validate and test, we're going to hold those all the way until the very end when we've made a model. Then we can decide if that model's any good or not. Looking at validate and test, those are out of sample data sets. So this allows us to test a model that we've built on the train, okay? And validate and test will approximate the model seeing brand new data in the world, right? Because it hasn't trained on them. So notice when I take the training set, it's going to be a little bit smaller actually. So the training data set has 1,029 rows versus the original data frame, which was 1,400. So it looks like it's about 3/4. And also the trained data set is randomized on the index. So this splitting the data also shuffled my training data so that it picks up on meaningful patterns, not accidental patterns. Like what if the pattern of the index had something with, it picked up on that. We don't want it to do that. Okay. Let's see. I gotta run my clean again. Give me just a sec. Gotta run my clean, and then I'll split. There we go. Okay, cool. So we have 0s and 1s for attrition. At this point, let's take a little look at the visual exploration of our data. And this part of the workshop, I want to be very transparent. I am cutting lots and lots of corners here on the data exploration phase. In working with this data set, I would want to spend as much time as I could analyzing the data, charting things out, looking visually for correlations like Xavier was talking about, doing statistical testing to measure the strength of those relationships. So I'm cutting tons of corners with the Explore phase for the purpose of this workshop, right? Now in Codeup itself, we do tons of exploratory data analysis on all of our data sets. And what exploratory data analysis is doing is trying to figure out what does each variable look like in detail. Right? How do those variables relate to one another? What's the interplay there? And where can we find any takeaways already just by exploring the data and charting things out? And the main tasks, the main responsibilities of exploratory data analysis, it's exploring the visuals and the relationships of data, exploring the descriptive stats, and also doing statistical testing, right? And hypothesis testing. And I have a typo here where I made them the same word, right? So let's take a look. Let's take a look at some of our data. We look at the monthly income of our training data, and we see the following things. We see the average monthly income, the standard deviation, in general, the measure of spread, how far away most of the values are from the mean. We see the minimum, looks like somebody's clocking in at 1,009, and then we see the maximum income at this company, which is almost 20,000. And then the 25, 50, and 75, the 50%, this is the median. So the median is the middle point. If we sort all the values, it's the middle value. It's not the same thing as the average, but it's the ordinal middle. And then the 25% mark, that's called the first quarter. That's the middle of the middle. So the 25% is between minimum and 50%. And then that 75% mark, that's between the median and the maximum. Okay, so we get to know a little bit about it. Let's visualize this monthly income. What does this look like? Well, it looks like there's a couple of folks at this company. There's almost 50 folks who are just making crazy money at this company. They're making 20,000 a month, right? That's just crazy. There's a 15,000 a month. That's pretty low. And most folks at the company are on the lower end of the values, and then things taper off pretty rapidly, right? Pretty rapidly. So what we're doing at this stage of the exploratory data analysis is getting a sense of a distribution, right? We're looking at how income is distributed, and we can look at other columns as well. Like we could look at how, like the work-life balance is distributed or the education is distributed. We can take a look at that real quick. Let's take a look at the education. I'm going to look at a histogram. So I'm looking at the distribution of education. 5 if it's a PhD, 4 is a master's, 3 is a bachelor's, 2 is some college, 1 is no college. So it looks like most of the folks at the company have a bachelor's or a master's, and there's more people with some college or no college than people with PhDs at this company, right? We can also take a look at, what is the proportion? What is the proportion of people who stayed at the company? That's a 0. They didn't leave. Attrition means somebody leaves a company, right? The number of folks that left was 180 in the last year. So at this point in the game, let's figure out in this consulting company, 20% of the employees left in a year, 21%. So is that normal for this company? This is a good part to ask ourselves, is this normal for this company? Is this normal for the industry? Right? If this is like real estate or life insurance, turnover happens really at really, really high rates, right? Or is this indicative of a challenge at a company or some, can we improve this? And based on the analysis, can we find folks who are statistically similar to those who have left, who we should talk to and make sure that they're happy and not just saying they're happy, right? So let's keep going. I'm going to take a look at account. We just did this, but this is a prettier way of looking at the education levels, and we're looking at the count. So the count of employees. So there's nearly 600 folks with a bachelor's at this company, around 400 with a master's. Right? And we can look at some of our other columns. The work-life balance. Most folks are saying that it's pretty darn good, a 3. And the second highest is a 2. Okay, well, what about job satisfaction? Man, looks like everybody is reporting that they are very, very satisfied with their job at this company, which is wild, right? Because we've got 3s and 4s on job satisfaction. We've got nice 3s, but not that many 4s on work-life balance. But there's 21% attrition, right? So we're trying to, at this explore stage, again, this isn't a data visualization workshop, but I do want to provide a little guidance here. Let's take a look at things like how do the incomes, here's a good one. Let's pay attention to the monthly income levels. That's on the y-axis here. On the x-axis, we're comparing the blue is people who stayed, the orange is people who left the company. And this visual that we're looking at here is called a box plot. It's a way of measuring a distribution. And what we're seeing here is the middle line through the box is the median. And the median is another way of measuring the middle of a data set, just like mean or average is a way of measuring the middle. And we also measure the spread. So you remember the 25 and 75 point marks, right? That's the top of this box is the 75%, the third quartile, the bottom of the box is the first quartile. And so looking at this, it looks like the data supports a hypothesis that income and attrition might be related at this particular company, right? Because we see the folks who left the company, their salary range is tighter and it's lower. And these little dots that are way out are outliers, right? So there's still some outliers on the super high income on the attrition, but it's not as many as the folks who stayed at the company, right? So I think this chart right here, this box plot is pretty telling about this particular data set, right? I'm going to make another visual real quick. And what we're looking at on the y-axis is the monthly income, right? The x-axis is the 1, 2, 3, 4 job satisfaction. And the orange is the people who left the company, the blue is the people who stayed. And what I find really interesting about this is that there's not that much variance between the different income levels and the job satisfaction, right? There's when we focus on the blue bars, see how the blue bars, they kind of go down a little bit, but it's not super significant. The orange bars go up, go down, go up, but it's not super significant. But what leaps off of the screen here is the gap between the monthly incomes of the folks who stayed versus the folks who left the company, right? That's a huge gap. Right, for the folks, for most of these, it looks, just eyeballing that, it looks somewhere in the realm of $2,000 in monthly income, right? So this being said, we could do a lot of workshops actually on data visualization. This is just the tip of the iceberg. And again, I am cutting lots and lots of corners to fit in the modeling that we'll get into in the remaining 13 minutes, okay? So we can do tons of exploration, and remember that this is just the tip of the iceberg. We're trying to get to building a model where we could build a predictor, right? So the predictor that we're going to be making is called a decision tree, and a decision tree asks a whole bunch of yes or no questions about our data. Based on those yes or no questions, it's able to narrow things down. It's just like that parlor game or that road trip game called 20 Questions, where we try to use our features and questions about those features to discover the outcome in our target variable. And here's an example. This is a visualization for a different data set. This is measuring flower measurements, measurements of the petals, petal length and petal width of flowers of irises. So based on, it's like asking yes or no questions. Is the petal length greater than this measurement? Yes, it's a setosa type of iris. If it's not, then we ask another question. Is the petal width a different measurement than length? Is that less than 1.5 centimeters? If it is, then we're sitting on a versicolor iris or not a virginica iris. So in the space of this data, and what a decision tree is doing is drawing horizontal and vertical lines across multiple dimensions. So not just length and width, but however many columns we have in our data. And we see here that this model is pretty good, right? That first decision point that split the setosas from the other two virginica and versicolors is pretty good. I don't see any blue X's on the wrong side. I don't see any brown or orange X's on the wrong side, which is good. The bar that measures the petal width, well, I see a brown X on the left. I see an orange X for versicolor on the right. So the X's are the actual pieces of data. Those are the real measurements for the real flowers. The green lines are the rules that the machine learning algorithm learned based on the data set. This is the pattern recognition, right? So we see that there's some misclassification with the orange and the brown. And that's going to happen with every model. And folks, I'm here to tell you that is because models are maps. That's all a model is. The reality, the data points, that's the terrain, that's the actual ground. But the model is a map for trying to understand the ground. So models aren't perfect, but they are representations of the map, of the terrain. Let's keep going. It's time to build a model. We've cleaned up our data, and now it's time to define our target variable. Our target variable is attrition. That's the thing we're trying to predict. So we set that to be our Y value. And then what are the columns that we have to make predictions on? We have income, education, work-life balance, job satisfaction, travel, frequent travel or not, percent salary hike, right? So we have our X's and our Y's. And at this point, we are at the 81-minute mark in our 90 minutes to machine learning. 81 minutes, we just made a model. This line of code right here, these two lines of code, are deceptively easy. It is real dang easy to build a machine learning model. How do we do it? Well, we decided I'm going to make a decision tree classifier. There's many different types of models, more than I can get into with y'all today. We have time in the Codeup course to talk about many of our models. Decision tree classifier is our model, and I'm fitting that model on the training data. So in fact, getting to the part where we build a machine learning model is 2 lines of code if our data is already done and ready and prepped. So there's a lot more to both machine learning and data science than building a model, but the nice part is this is the pretty simple part, and we're seeing in the output of this model that we're accepting in a whole bunch of model defaults. You see all of these different arguments and parameters in here, the depth, the criterion, the max leaf nodes. I'm not going to go into all of these things. These are different ways of tuning, fine-tuning our model. We will talk about a good measure of those in most of these defaults are pretty good. But yeah, building a model is actually pretty easy. You just go model.fit, right? But that's not the entire story. Let's talk about the rest of the story. Now we need to figure out, okay, based on this model, what are the probabilities that the model is correct? 70% chance that the model is correct on one row. Gosh, a 29% chance that the model is correct on another observation, 2/3 chance that it's correct on another, 1/3 chance that it's correct on another observation, a 90% chance, right? So let's take our model that we've and see how good it is. The way that we're going to measure the model's usefulness in our workshop today is with accuracy. There are many, many ways of measuring how well a model performs. We're just going to focus on one today. And so when I run this, what I'm looking at is I'm looking at the accuracy score. So I'm saying, hey, decision tree model, hey, model. And this is all through Python. Give me your score. And score is going to give us back the accuracy. And accuracy mathematically is determined by the number of true positives plus the number of true negatives as a ratio of all of the observations. So true positives and true negatives. Let's make a visual for that. True positives in this cases are, if we're going to compare to this visual, blue X's underneath this green line. Those are true positives, right? And the brown X's or the orange X's that are on the right side, those are also true negatives or true positives, right? When we have an orange on the brown side or a brown X on the orange side, we have a misclassification, right? So that can hurt our accuracy. So looking at how well does our model perform on our training data, actually need to remove the percent symbol. It's not 89.89%. It is actually 89%. I need to remove this percent symbol here. That's pretty good. That's pretty good, right? But we need to see how well the model performs on data that it has never seen before. So how we do that is I go to that, you remember that validate data that we set aside for later for that out of sample data set? Again, we split the data very early in our process so that we could have in sample and out of sample. We build our statistical models, our machine learning models on in sample. We evaluate them on out of sample. So now I'm saying, hey, let's evaluate this on out of sample and see how well it does. 83%. That's not bad. That's not bad. 83%. It's less than 89%. So what we see is some degradation in performance when the model sees brand new data. And when a model performs well on training and a little less well, or even dramatically worse on out of sample data, we call that overfit. So the model is overfit. And it's overfit by just a little bit. But this is the part of the episode where if this is your first day or your first project on a data science team, you definitely want to talk to your colleagues and say, hey, I made a model, I trained a decision tree, I got almost 90%, but then on my out of sample data, my validate, I got almost like 80%. What can I do to fix this? And the quick answer is from the colleagues would be, oh, didn't you go to Codeup? Didn't they teach you how to fix this kind of problem because you have an overfit model? And the answer is we do, right? That is more stuff than I can fit into 90 minutes, however. So we have a model. It's better than guessing, right? Because guessing, if somebody was based on the historic attrition rate, was like 20%. So if this is 17%, it's still better than guessing or just like rolling the dice based on historical data. So the model is valuable, but we can probably do better. We can probably do better on this model. It is definitely overfit, and yeah, covering all the ways to evaluate models and improve them so that we get good performance on out of sample data as well as in sample data. That's what the rest of the Codeup course covers, right? Along with Python and SQL and data visualization, data storytelling, exploratory data analysis. So here's my parting takeaways for you. Because we've got 3 minutes left, right? So valuable machine learning models that work perfectly the first time are something that only happen in the movies or in tutorials. And so I've given you an example of a tutorial where things were going pretty well. We have a good model. It could be better, but the things that we can do to make it better are stuff we don't have time for today. So there's always more room for exploratory data analysis. Make sure to get this message today, models aren't enough. We don't just need a model, we need effective models. And a handful of ways that we can make better models that we cover over and over and over in Codeup are the following topics. Again, you don't need a PhD or a master's degree in statistics to start with data science and machine learning at Codeup. Here are some of the topics that we cover to get you on par where you can be contributing to teams in that way: hypothesis testing, feature engineering, handling imbalanced data, removing and identifying outliers, different types of models. I only gave you all one type of model, and there's many, there's dozens, if not hundreds of types of different models. I talked a little bit about hyperparameters, which are like the model's dials that you can tune. And then we can also do dimensionality reduction as well as other tasks for addressing underfit or overfit models. So whew, we covered a lot in 90 minutes. We pulled up we introduced data science, machine learning. We introduced Codeup, the Codeup program. Why Codeup? We then did a very small end-to-end data science project where we ended up with a very classic problem. An overfit machine learning model is a classic problem. Getting this performance to be better, actually getting both of these numbers to be better is entirely possible. And we have the tools and technologies, just a little bit more than I have time to get into with 90 minutes. So there you have it, folks. That is 90 minutes to machine learning. My recommendations on next steps, my recommendation, personal recommendation here, I am very biased, right? I'm very, very biased to Codeup because we have results. We produce results for our students, right? So if you're looking to get into this field, whatever program you're looking for, ask about the results, demand to see the results. How are people getting hired? Because in the industry, it's not just can you pay for the class, but does the class get you a job? Does the class get you a career, right? And through Codeup, you can, in fact, start learning in data science and machine learning without a PhD or a master's degree. Now, I say that not, some folks have come into the program with a PhD or a master's degree, right? It happens. It's going to help. But it's not a gate. So my advice to you is apply to Codeup. If you liked what you saw that we could do together in 90 minutes, imagine what we could do in 6 months together.